Okay, so think about when you pull up a map app on your phone, right?
Mm.
You expect your destination to be this like highly specific pin. You zoom all the way in on a restaurant or a street corner, and there it is.
Right.
It's just a single one-dimensional point on the screen.
Exact.
Definitive. You know exactly where you're heading.
Yeah, it gives you that really comforting sense of geometric certainty, like this is a specific location in space that I can physically occupy.
Exactly. But when you zoom out past the Earth, past the galaxy, straight into the center of a black hole, that pinpoint GPS dot is a complete lie.
It really is.
We're looking at a cosmic destination today that, well, you've probably been told your entire life is a single infinitely dense point.
Right, the classic singularity.
Yeah, the singularity. And that premise, the idea of the zero-dimensional dot sitting to the very bottom of the gravity well, is completely dismantled in this highly disruptive 2026 physics paper that we are doing a deep dive on today.
Yeah, it's by Andrew J.S. Hamilton and Tyler McMicken.
Right. And they've basically proven that the singularity isn't a dot at all. It's actually a massive shifting surface.
Which is, I mean, it's wild. It fundamentally rewrites the geometry of the most extreme places in the universe.
It's not just a small technical correction, right? Like, this changes everything.
Oh, absolutely. We are not just talking about, mathematical pedantry here. Changing the singularity from a point to a two-dimensional surface, it destroys the classic sci-fi dream of wormholes, for one.
R.I.P. to wormholes.
Right. Totally.
Yeah.
And most importantly, it radically changes where the ultimate secrets of quantum gravity are actually hiding.
Okay, so to really wrap our heads around why the singularity isn't a point, the paper starts us off with like the simplest mathematical scenario, right?
Yeah, the spherical, non-rotating Schwarzschild black hole.
Right. So we have to imagine this thought experiment where two objects fall into it at the exact same time. Let's call them a blue infaller and a purple infaller.
I like it. Blue and purple.
So they drop straight in simultaneously,
Yeah.
but from completely opposite sides of the black hole. Now, basic spatial intuition dictates that if they fall in at the exact same time, heading toward a central coordinate, they have to eventually bump into each other at the exact center.
Right, they meet in the middle.
Right. But why doesn't that happen?
Well, so that intuition completely breaks down once you cross the event horizon because the actual nature of space itself changes.
The space changes.
Yeah. We know the defining feature of the interior geometry is that space-time itself is falling inward faster than the speed of light.
Faster than light.
Yeah. The spatial metric itself is plummeting, and it drags the fundamental light cones down with it.
Okay, wait, let me make sure I've got this. So the special relativistic rule that nothing can move through space faster than light, that still holds, right?
Yes, absolutely.
But space-time itself is allowed to do whatever general relativity prescribes. So if I'm the blue infaller and I shine a flashlight sideways, like to try and signal the purple infaller on the other side.
That sideways beam of light gets dragged downward.
And gets dragged.
Yeah, it can't travel purely horizontally anymore. The light cones literally tip inward.
Wow.
And as you fall closer to the center, the space-time river accelerates. The inward flow becomes so severe that your light gets dragged down on this increasingly steep diagonal.
So it's fighting a current it can't beat.
Exactly. And the paper maps this out mathematically. They show that the boundary of what you can actually see, so your causal past and future, it forms the shape of a cardioid.
A cardioid.
Yeah, our heart shape.
Right.
And as you fall deeper into the gravity well, the edges of this heart shape, this cardioid, they fold in on you.
Okay, so I'm picturing like a pair of blinders.
Yeah.
Like if you put on horse blinders, but they get mechanically tighter and tighter the deeper you fall,
Yeah.
until your visual field is restricted to just this tiny sliver staring straight ahead.
That is exactly it. Your field of causal interaction shrinks exponentially. So by the time the blue infaller is nearing the central coordinate, their ability to send or receive a light signal has narrowed so drastically that they lose all visual contact with the purple infaller.
And this happens before they hit the center.
Long before either of them reaches the center, they literally cannot reach each other with a light signal, no matter how powerful the laser is.
Wait, I'm kind of stuck on the math here, though.
Yeah.
Because doesn't the famous Schwarzschild metric literally dictate that the spatial radius, r, goes to 0 at the center?
It does. The equation says r equals 0.
Right. So if their spatial distance is 0, how can they not be close to each other? Like, how do they not physically collide?
Okay, so we have to separate the concept of spatially close from causally close.
Spatially close versus causally close.
Right. General relativity is incredibly rigid about this distinction. In our standard, everyday Euclidean experience, if two things are spatially right next to each other, a signal can pass between them almost instantly. But in curved spacetime, causal distance is strictly measured by the shortest path a light signal can take between two events.
Oh, I see.
Yeah.
Because if light can't traverse the gap, then no information or physical matter can traverse the gap either.
Exactly. And even though the spatial radius, r, is shrinking to zero, the spacetime is falling inward so violently that the shortest possible path for a light signal between the blue and purple infallers does not go to zero.
Wow.
The light simply cannot fight the inward flow to bridge the gap between them. Therefore, they land in completely causally disconnected places.
That is mind-bending.
Right. If 2 points are causally disconnected, like, if an event at point A cannot possibly influence an event at point B, they cannot be the same physical point in space.
I mean, the math says r equals 0, so our brains automatically picture a single dot.
Of course.
But relativity actually demands this extended two-dimensional surface where all the points on that surface are causally walled off from one another.
Yeah, you are left with an entire landscape of coordinates that arrive at the end of time utterly alone.
Utterly alone. That's kind of haunting, actually.
It really is.
Which I guess naturally leads to the visual experience, right? Like, what does this actually look like?
Oh, this is the best part.
Yeah, because the paper features these incredible ray-traced optical models of what an infaller would actually see as they approach this surface. And it entirely defies the standard visualization of a black hole as, like, this dark, empty pit.
Right. We always see it as a drain in movies.
Exactly. But when you look down, according to the paper, you aren't actually seeing the event horizon below you. You're seeing the past horizon.
The illusory horizon.
Yeah, can you explain that? Because that threw me a bit.
Sure. So you're looking at the exponentially dimming, red-shifting image of the original star that collapsed to form the black hole, which might have been, billions of years ago.
So wait, the star is still there? Visually?
Visually, yes. Because space-time is falling inward faster than light, you are always looking at photons that were emitted above you, which are now falling down with you.
Okay, so you never actually catch up to that light.
No, you don't.
The ghost of the collapsed star just sort of stays ahead of you, getting dimmer and redder, like stretching out into infrared and beyond.
Right.
And then, as you fall through the actual event horizon, the optical geometry does something completely wild. The horizon appears to split into two.
Yes.
Yeah.
Because you don't actually visually register the event horizon until you have already passed through it.
Which is so counterintuitive.
I know. But once you cross that threshold, the light from the outside universe aberrates, and the event horizon suddenly appears above you, like this dark sky closing you in.
Oh, wow.
Meanwhile, that past horizon, the fading image of the dead star, is still locked below you.
So you have a sky above you and a star below you.
Exactly.
And as you approach the singularity itself, the ray-traced models show you never hit a central dot. The extreme diverging tidal forces like gravity just pulling and stretching light in wildly different directions, it actually flattens your visual field.
It flattens it completely.
It forms this infinite flat plane.
Yeah, the tidal forces aberrate the incoming photons so severely that the visual manifestation of the singularity becomes a completely flat, infinite wall. The two horizons, the event horizon closing in from above and the past horizon below, they basically appear to converge toward this flat plane.
Okay, so it's kind of like chasing a mirage on a hot highway.
Oh, that's a great way to put it.
Yeah, like you keep falling toward the ghost of this dead star, expecting to hit a speck of dust at the bottom of a funnel.
Yeah.
But the whole universe just flattens out into a wall in front of you.
Yeah, falling into a black hole isn't this claustrophobic crushing into a point. It is a dynamic optical light show of shifting, flattening geometries. It completely challenges our basic human perception of boundaries and shapes and dimensionality.
It's just wild. But wait, okay, all of this assumes a dead stationary black hole.
Right, a perfect Schwarzschild vacuum.
And we know that real astronomical black holes out in the universe, like Cygnus X1, for example, they are spinning. They're spinning at something like 95% of their maximum possible speed.
Yeah, they are spinning incredibly fast.
So if a black hole is rotating that fast, doesn't the centrifugal source push back against that inward flow of space? Like, doesn't that prevent this whole causal disconnection thing?
So the rotation heavily alters the geometry, introducing the Kerr metric. And historically, the Kerr metric promised some of the most incredible phenomena in theoretical physics.
Right.
The idealized math for a spinning black hole suggests it has two horizons, an outer event horizon and an inner Cauchy horizon.
And that inner horizon is basically the gateway to, like, half of all science fiction.
Oh, absolutely.
Because the Kerr equations suggest that inside a spinning black hole, centrifugal force slows the inward flow of space down enough that the singularity stretches into a one-dimensional ring.
Iron ring singularity, yeah.
And supposedly, if you fly through the center of that ring, you bypass the singularity entirely and enter a wormhole connecting to a white hole. Or you can even travel backward in time. I mean, the math literally allows for closed time-like curves.
Yeah, the mathematical solutions derived by Roy Kerr and Brandon Carter in the 60s, they absolutely allow for causality violations.
So we can time travel.
Well,
So,
no. I know, I'm sorry. But the paper makes this rigorous case for why those wormholes and time machines are strictly mathematical fantasies. Because the beautiful, elegant math of the Kerr wormhole relies on one critical, totally fatal assumption.
Which is?
It assumes the black hole exists in a perfect, eternal vacuum.
Okay, completely empty space forever, which obviously doesn't exist.
Right.
Black holes eat stars, gas, dust. But the paper claims that even a tiny amount of light, even just background radiation, ruins the math entirely. And I was genuinely stuck here when I was reading it.
It's hard to grasp, for sure.
Because we're talking about a single photon of cosmic microwave background radiation compared to a supermassive black hole with the mass of 1 billion suns. A photon is literally less than a drop in the ocean.
Yeah.
So how does a single photon mathematically destroy a wormhole?
Okay, so it comes down to a phenomenon known as the Poisson-Israel mass inflation instability.
The mass inflation instability.
Okay.
Yeah.
When you introduce even a single photon into the rotating black hole, you disturb the delicate balance at the inner horizon. Remember, space is flowing inward from the outer horizon, but inside the inner horizon, centrifugal force is pushing outward.
Okay, so you have two streams of light. One stream is falling inward, and another stream is effectively trapped, trying to move outward against the flow.
Exactly. The inner horizon acts as a Cauchy horizon, which is basically a boundary where all the light from the entire future of the outside universe piles up.
Oh, wow.
Right. So as these outgoing and ingoing streams of light are driven together at the inner horizon, the immense gravity causes them to see each other as infinitely blue-shifted.
So their wavelengths compress so much that their relative energy skyrockets to infinity.
Yes.
It's like a cosmic crossfire.
An infinite energy crossflow. And this crossflow completely destabilizes the inner horizon. The local mass and the tidal forces inside the black hole, they just exponentiate.
They just blow up.
Yeah, they blow up to unimaginable infinite levels in a fraction of a second. The black hole essentially chokes on its own internal energy dynamics.
Which triggers what the paper refers to as the Belinsky-Kalatnikov-Lifshitz collapse.
Right.
The BKL collapse.
The BKL collapse, yeah.
But how does that actually work? Because when I hear collapse, I just think, okay, gravity just crushes everything into a pancake.
It's way weirder than that. The BKL collapse is highly chaotic and anisotropic. Space-time doesn't just crush you uniformly, it oscillates wildly.
Oscillates.
Yeah. Gravity stretches the geometry in two directions while violently crushing it in a third, and then the axes swap. It stretches and crushes, vibrating faster and faster in what physicists call a mixed-master dynamic.
A mixed-master dynamic.
Like a blender.
Yeah, kind of. It vibrates until the geometry itself shatters.
Okay, so the inner horizon just violently crashes down. The ring singularity, the wormholes, the time machines, they are all crushed out of existence by this oscillating wall of infinite energy before they can even form. Exactly. The interior geometry is fundamentally truncated. The infinite energy crossfire ensures that you never reach the fantastical Kerr ring singularity. Instead, you hit a space-like singular surface.
Leaving you with a causally disconnected two-dimensional plane, exactly like we saw in the non-rotating case.
Exactly the same.
So whether a black hole is sitting perfectly still or spinning at nearly the speed of light, all roads lead to a singular surface.
Yes.
The wormhole is dead. You just hit a two-dimensional wall.
Sorry to ruin the sci-fi for you.
I know, it hurts a little. But this actually brings us to the ultimate question of the paper. Why does this geometric distinction, like having a surface instead of a point, why does that matter so heavily to the future of quantum physics?
Because the implications for quantum gravity are just profound, specifically regarding the information paradox.
Right, the information paradox.
Yeah, we have spent decades trying to resolve what happens to information, you know, the quantum states of matter, when it falls into a black hole. Modern string theorists, heavily influenced by Stephen Hawking, They have long relied on the holographic principle.
Okay, the holographic principle, that's the idea that the three-dimensional information of everything that falls into the black hole is mathematically encoded on its two-dimensional outer boundary.
The event horizon.
Right, the event horizon.
The prevailing theory has been that the event horizon acts as this sort of holographic film. But Hamilton and McMakin make a really bold claim here. They say the quantum states do not live on the event horizon.
Which, I mean, that logically tracks with the visual models we discussed earlier, right?
Exactly.
Because if an infaller drops past the event horizon, they don't see it, they don't hit a firewall of quantum data, they literally don't feel anything unusual at all. The event horizon is essentially a mathematical phantom to the person crossing it.
It's totally illusory to them, yes.
So, okay, if I could use an analogy here.
Go for it.
If we think of a black hole as an exclusive nightclub,
Okay.
we've spent decades assuming the guest list, all the vital information, is written on the bouncer at the door, the event horizon.
Right.
But this paper is arguing that the bouncer is an optical illusion. The bouncer isn't holding the information. The actual party is happening strictly on the dance floor at the very bottom of the club, the singular surface.
I love that analogy. Yes. The party is on the dance floor. And because the true quantum energy is entirely concentrated on that dance floor, the physics there must strictly obey the rules of quantum mechanics.
Right.
Specifically, it must adhere to unitarity.
Unitarity.
Yeah, unitarity is the absolute requirement that information cannot be destroyed. The probabilities of all possible quantum outcomes must always add up to 100%.
But classical general relativity, I mean, originally it modeled the singularity as a boundary where time just ends, right? Like an exit into nothing.
Exactly. And quantum mechanics completely rejects the idea of an exit into nothing because that deletes information from the universe.
So how does the paper resolve that?
Well, if the singularity is a two-dimensional surface and it must preserve information to satisfy unitarity, it cannot be a dead boundary.
Right.
The singular surface must be a physically active region. The paper dictates that the singular surface is actually a roiling hot atmosphere of trapped Hawking radiation.
Wait, I thought Hawking radiation was specifically the mechanism that allows black holes to slowly evaporate over, like, trillions of years.
It is.
It's the thermal radiation that manages to leak out past the event horizon.
Yes, but that escaping radiation is only a microscopic fraction of the total picture.
Oh, really?
Yeah. The vast majority of the Hawking radiation generated by the intense curvature of a black hole is created deep inside the event horizon.
Inside.
Yes. And because space-time is flowing inward faster than light, that radiation cannot escape to the outside universe. It is violently dragged downward, forced back onto the singular surface.
Wow, so the surface is just constantly bathing in an extreme thermal bath of its own trapped radiation.
Precisely. It creates a closed thermodynamic system. Because the radiation is trapped against this two-dimensional boundary, the singular surface rapidly reaches a state of thermodynamic equilibrium.
So it's basically cooking itself.
Yeah. The surface and its trapped radiation co-evolve unitarily. When a particle falls in, its quantum information isn't crushed out of existence at a microscopic point.
Because there is no point.
Right. Its quantum entanglement is shared across this expansive, hot, two-dimensional surface, mixing continuously with all that trapped radiation.
So we have this completely new paradigm for visualizing the most extreme objects in space.
We really do.
The center of the black hole is not a point. It is a causally disconnected, flat-appearing two-dimensional surface. And the event horizon isn't where the holographic magic happens.
Nope.
The true quantum nature of the black hole resides at this singular surface, existing in a fiery, trapped thermodynamic equilibrium.
Yeah. We have to stop hyperfixating on the event horizon and start dedicating our mathematical models to understanding the thermodynamics of this two-dimensional hot surface. The true intersection of general relativity and quantum mechanics lies in understanding how information spreads across that causally disconnected plane.
Which leaves you with an incredible conceptual leap. I mean, it really blew my mind when I got to the end of the paper.
Oh, I know exactly where you're going with this.
Because if singularities are not infinitely dense, zero-dimensional dots, but are actually expansive, two-dimensional surfaces locked in thermodynamic equilibrium.
Yeah.
It completely reframes how we look at the origin of everything.
It really does.
We always picture our own universe starting from a single, infinitely small dot, the Big Bang. But if the math of ultimate collapse in this paper holds up, it means the math of the ultimate beginning might mirror it, right?
Exactly. The geometry of the end heavily implies the geometry of the beginning.
So you and I, the galaxy, the entire observable cosmos, we might not have expanded from a microscopic point, We might have expanded from a hot, roiling, two-dimensional sheet of quantum states.
Yeah, the Big Bang didn't need to be a pinprick. It could have been a vast surface of quantum information that just unfolded into the four-dimensional space-time we inhabit today.
It's just so much to think about. Next time you pull up that map app on your phone and you see that tiny, perfectly defined pin, remember that the universe at its absolute extremes doesn't operate on points.
It really doesn't?
Look up at the night sky and reconsider the physics hiding in the dark. The ultimate destinations in our cosmos aren't periods at the end of a sentence. They are entire landscapes waiting to be explored. Thanks for coming on this deep dive with us.